Hello and welcome to this next lecture on fundamentals of acoustics. We are looking at measures of sound, and within that we are looking at frequency analysis, okay, and we were discussing about narrowband analysis and how narrowband analysis can be expensive and maybe a little too fine for the job, okay. So now let us say a certain machine has come, okay, or your company makes a certain machine, okay, then it may just be enough to know that in this frequency band how much is the noise, in a slightly neighboring band how much is the noise, and the next band how much is the noise. It may be adequate to know this information and not too fine, not in a narrow band sense, okay. So if you suppose somebody says that your machine is loud between 100 and 500 hertz, sometimes that may be adequate, or say your machine is loud between 3 kilohertz and 4 kilohertz, and then that also may be sufficient for you to characterize, okay. If anything more specific is needed, if there is some trouble, there is some issue, there is some instability causing damage, then you can go to narrowband analysis. But in a general way, suppose you are making this machine, 100 machines a day are being made, and then you just want to characterize each fellow and put a number, okay, then this kind of broad analysis is adequate, okay. So now that leads us to, as opposed to constant bandwidth analysis, it leads us to constant percent bandwidth analysis, constant percentage bandwidth, okay. And in some way our human hearing works on this, human hearing, works on this idea, okay. So if you are musically inclined, then you have this musical scale that starts with a sa, re, ga, ma, pa, dha, ni, sa, and to our human ear this sa and the higher sa, which is just one octave above, one octave is double frequency, okay. So if this is 250 hertz, then that is 500 hertz, okay. Double frequency, they seem similar, okay. So if we break up our frequency, okay, our frequency range, suppose we break it up in octaves, okay. So let us say I have 100 over here, then I have 200 over here, hertz, okay, I am talking hertz, then 400 maybe about here, then maybe 800 is here, okay, and then 1600 maybe here or something like that, even more, okay. So we characterize our machine, we call this band 1, we call this band 2, we call this band 3, we call this band 4, and so forth, and we characterize the machine, okay. Now one thing what happens is very quickly it becomes very rough, okay. So here we have suddenly 400 hertz band, okay, then here we have 800 hertz band, okay. On one hand we do not want a narrow band because it is expensive, but on the other hand we do not want to lose out the characteristic also, okay. Suppose there are three frequencies that are offending in this range, okay, then all you know is that in an 800 hertz band something is going wrong. Okay. So you have a huge range where so you don't know, you don't have a clue where what is going wrong. Okay. So now to correct this part, okay, instead of octave bands, we have devised 1/3 octave bands. Third octave bands. Okay. So what are third octave bands? What are octave bands? Suppose first of all, octave bands. I am just giving an example. Okay. So if I have a center frequency, let us say f, okay, f as a center frequency, okay, then the next center frequency will be twice that. Okay, and the next center frequency will be twice of that. Let's say the FC0, FC1, what is it, FC0, twice FC0, then twice into twice, 4 FC0, and then 8 FC0 and so forth. Okay. So then there is a band around this, there is a frequency band around FC0, there is a frequency band around twice FC0. So twice FC0 represents a band. Okay. Then similarly 4 FC0 is fully representing another band, a higher band, and so forth. So the bands are characterized in terms of the center frequency value. Okay. Now I said this is very rough, very quickly. So what are third octave bands? What are third octave bands? They are, if we choose a certain value f0 or center frequency, okay, the higher frequency is 2 to the power 1/6 of Fc, this is F higher, and the lower is 2 to the power minus 1/6 of Fc. So this is called F low, Fc. So that the ratio of Fh by Fl is 2 to the power 1/3. Okay, here it was 2, here it was 2, okay, here it is 2 to the power 1/3. Okay. Now these third octave bands have been standardized. Okay. You see how we are bringing in the frequency content. We said RMS loses the frequency content, but we said mean square can be added, then mean square within bands, if you find, they can be added. Then bands, we spoke of narrow band, and narrow band as being a little fine or expensive. Then narrow bands are constant bandwidths. Instead of that, we went to constant percentage bandwidths. That means the ratio of the higher and lower frequency are constant. Okay. So the rough one example is octave bands. Then we went to third octave bands. Okay. Now these third octave bands are standardized. Okay. What is the standardization? The standardization is I will not write all of them, but one of the center frequencies is 100 hertz. Okay, even before that. So it turns out that 2 to the power 1/3 value to the power 10 is approximately 10. Okay, it is very interesting. So that means what, if I have 100 hertz and if I have 10 times that, which is 1000 hertz, in between I can fit 10 third octave bands. I can fit 10 third octave bands using this rule, okay. So if we start these bands start at 25 or lower, okay, but it is unimportant. Suppose I have 100 hertz, okay, then it has a higher frequency 112 FH, F center, F lower. The F lower is 89.1. Then the next center frequency is 125. It has a higher band 141 and lower band 112, lower value 112. Then the next is 160, higher number is 178, lower number is 141. They are contiguous, and then you can continue, okay, like this, and 1000. The higher number is 1122, lower number is 891, and you can continue. Okay, these are standardized octave bands. Standardized. Okay, so now if in these bands, let us say in the 100 hertz band, okay, 100 hertz band, there are 4 machines. I am just giving an example, 4 machines, okay. Machine 1, M1, makes noise in the within the 100 hertz band, okay, and its value is 80 dB. Let us say sound pressure level for now, LP 80 dB. Then you have machine 2, and it exclusively makes sound only in the 125 hertz band, okay, this band, where exactly we do not know, but in that band, and it also makes, let us say, 80 dB, okay. Then M3, there is a third machine, it exclusively makes noise in the 160 hertz band, and M4, it exclusively makes sound in the 200 hertz band, and this value is, let us say, 83, and this value is 86 dB, okay. Now I could convert this into P square RMS, P square RMS by P square reference 1, similarly 2, similarly 3, similarly 4, and I could add them up and then again apply 10 log to the base 10, the summed up P square RMS by P square reference. I could do that, okay, or I can resort to dB arithmetic. Okay. If you add 80 plus 80, it is going to be 83 dB, okay, that is dB addition. So now 80 plus 80 gives me an 83 dB, 83 plus 83 gives me 86 dB, 86 plus 86 gives me 89 dB. So the average or the total sound when all 4 machines are operating, okay, is 89 dB, and this is what I mean by incoherent sources. incoherent sources. Okay, their frequency contents are not the same. Okay, this has a statistical meaning, but for now we will stick with the incoherent sources. Okay, so they together operating, the value is 89 dB. Okay. Now what I say is that I want to apply the human weighting or A weighting to this value. Okay. So if we apply A weighting to this value, we need corrections. Okay. So now I said the human ear, okay, D values sound at low frequencies. So the correction at, let me remove this slightly. Okay. So the correction, so I am writing A weight correction. So the A weight correction for 100 hertz band is minus 19.1 dB. Okay. The A weight correction for 125 hertz band is minus 16.1 dB. For the 160 hertz band is minus 13.4 dB. These are all standardized. Okay. And the 200 hertz band is minus 10.9 dB. Okay. So if I apply the corrections, okay, if I apply the correction for the 100 hertz, the correction gives me 60.9 dBA. Okay. So I have 80 and minus 19.1. Then the 125 hertz is 80 minus 16.1. So that is 63.9 dBA. Okay. The 160 hertz band, the correction is minus 13.4. So it comes to 69.6 dBA. And lastly the 200 hertz is minus 10.9. So you get 75.1 dBA. Okay. So now I have 60.9, 63.9, 69.6 and 75.1. Okay. Now if we add this up, it is approximately 76 dB, 76 point something. Okay. Here again we do the dB addition. We get this back to P square RMS by P square reference. Okay. 1, 2, 3, 4, we sum them up 1 to 4 and then we subject it to 10 log to the base 10 and so forth. Okay. Now just mind this, that this is as though each machine has been turned on. The 100 hertz machine was there, we turned on the 125, we turned on the 160, we turned on the 200 and so forth. Okay. So therefore we are adding it. Okay. But if it was the same machine and there were 4 locations, then that is an averaging process. Okay. In that averaging you will first sum this P square RMS by P reference square and you divide by 4. Okay. So one should distinguish the situation. Okay. The same machine in 4 locations had different sound, you want the average value. That is different from these 4 machines. It is as though each machine has been turned on and so the sound level is consistently going up. So that is what we have done over here. So here you do not divide by 4. Okay. Now just to give you, so that's dBA. So now I am sorry, this should have been dBA, my mistake. So this we call it dBA. Okay. So there are similarly B weightings and C weighting which are not popular now. All these were devised to model human hearing, but they are not popular, so not worth discussing. But you will hear B weighting, C weighting and so forth. Okay. C weighting amplifies higher sound, etc., etc. Okay. So now to just give you an idea, of power, okay, sound and sound power. If we have a Saturn rocket, I have taken this from the net. If you have a Saturn rocket, okay, then it produces 1 e to the power 6 watts, okay, that is watts of power, okay, and the power level, sound power level LW could be about 180 dB corresponding to this, okay, LW and watts, okay. So if on the other hand, if you have a turbojet engine, okay, it could produce 1 e to the power 4 watts, that is about 160 dB LW, okay. Or you have a bus horn or an auto horn, bus horn, okay, that could produce about 110 decibels or give or take, and the wattage is 0.1 watt. Yes, you see the wattage going down. Then if a human being voice, he shouts whatever to the maximum extent or some reasonable extent, the power LW may be 90 decibels, which is 0.001 watt, okay. And if somebody is whispering, that could be about 50 decibels, and the power is 1 e to the power minus 6 watts, okay. So compare this to the fact that let us say you have you are boiling water, okay, and the kettle is rated at some 1200 watts, and 1 liter of water, let us say it takes about 2 to 3 minutes, okay. So how much is the wattage and how much time it takes to boil 1 liter of water, and even in a voice that is shouting, how much is the wattage, you see, okay. So the raw power in sound is very low, okay. In another word, what it means is our ears are very sensitive, okay. I just saw some reports somewhere, just funny, okay. Some two scientists, they supplied 175 watts of sound power to boil an egg, okay, and this amounts to 142 decibels of LW, sound power level, okay. And if a single person, let us say he can deliver 80 decibels, which is quite high, of LW, sound power level. I keep writing LW because sound power level and sound pressure level, the initials are SPL. So let me say LW. Then this kind of requires about 1.6 million people to deliver 175 watts. Okay, that is how much little power we have in, as power in sound. Okay, and how sensitive our ears are. Next, what I am going to do is suppose we have a point source. Okay, and the intensity, so it radiates uniformly, it radiates sound uniformly. Okay, the intensity is power per unit area, which is power per unit area. Okay, so let us say we are talking at a distance of r, it is symmetric, therefore area is 4 pi r square. Okay, so now the RMS intensity or first of all time averaged intensity is 1/2 the real part of PV conjugate. This is the intensity. Now in the far field we get 1/2 the real part of P and V are related now. So P conjugate by rho c, this is particle velocity. So this is equal to 1/2 magnitude square of P by rho c. Okay, and this P is peak value. So this is equal to P square RMS by rho c. Okay, so then W by 4 pi r square is equal to P square RMS by rho c. Okay, so that my P square RMS is equal to rho c by 4 pi r square into W. Okay, so now P reference is 20 micropascals. Okay, and P square reference is 400 into 10 to the power minus 12 Pascal squared, or 4 into 10 to the power minus 10. Okay, so now if I do P square RMS by P square reference, that is equal to rho c by 4 pi r squared W by P square reference. Okay, or P square RMS by P square reference is equal to rho c by 4 pi r squared, and W reference, power reference, is also 10 to the power minus 12 watts. So this W by P square reference is 400 W reference. Okay. So if we now separate things out, P square RMS by P square reference is equal to rho C by 1600 pi W by W reference 1 over R squared. Now for air, rho is 1.21 kg per meter cube, then C will take it as about 340 meters per second, then rho C is about 415 units SI units, then rho C by 1600 pi is a small number 0.0826. Okay. So now if we do okay, we can do a slightly differently. We will do it this way: P square RMS by P square reference is equal to rho C by 400 into W by W reference into 1 by 4 pi R square. Okay. And this, so now if I do this 10 log to the base 10 on the left, that is equal to LP, that is equal to 10 log to the base 10 of rho C by 400, and this is approximately 1, okay, plus LW plus 10 log to the base 10 1 by 4 pi R square. Okay. So we are going to ignore this because log of 1 is nearly 0, so we are going to drop this value. So what I get is LP is equal to LW plus 10 log to the base 10 1 over 4 pi R square. Okay. So if I have a point source, which is radiating uniformly on down directions, or if I have moved into the far field, okay, of a source such that it is uniform in all directions, or uniform locally. Okay. So it has a 1 over R dependence in pressure. Okay. If that is the case, then SPL1 or LP1 is equal to LW plus 10 log to the base 10 1 over 4 pi R1 square. This is at a distance of R1, let's say, from the point source R1 far field. Then LP2 is equal to LW plus 10 log to the base 10. I have moved to a further location R2 1 by 4 pi R2 squared. Okay. Then LP2 minus LP1, okay, is 10 log to the base 10 1 by 4 pi r2 square minus 10 log to the base 10 1 by 4 pi r1 squared. Okay. So this becomes 10 log to the base 10 r1 squared by r2 squared. And if r2 is say twice r1, then I have 10 log to the base 10 of 1 by 4, which is minus 6 dB. So if you have strictly a point source and you have doubled your distance, you are at one distance and you doubled your distance, the sound pressure level or intensity level also will drop by 6 dB. So you can hold this as a rule of thumb. Okay. Now the other point I wanted to mention, just for those who want a quick idea, okay, is this in a normal voice content, let's say a normal voice, okay, the sound pressure level, the Pascal level above the ambient could range from 2 into 10 to the power minus 3 to 0.02 pascals. This is above the mean, okay, normal, okay. If you have an anechoic chamber, we have spoken of an anechoic chamber, right? Anechoic chamber, then that can be 6.8 into 10 to the power minus 6 pascals, which is minus 9.4 dB, because it is softer than reference sound level. Okay. Let us say you are on traffic on some busy day, okay, and you are say 10 meters away, at a distance of 10 meters away, okay. So the pressure you could experience is about 0.6 pascals, which could be about 90 dB, okay. Now the threshold of pain, okay, so if the sound goes louder, it could cause pain. Threshold of pain, okay, is 200 pascals, which is about 140 dB sound pressure level, LP, okay. A jet engine, depending on the distance, it could be about 600 pascals, which could be about 150 decibels, and so it is very loud, okay. And let us say busy shop floor, lot of machines are running, busy shop floor, milling, drilling, all the machines are running simultaneously. You could have about 80 to 90 decibels. So that is about 0.6 pascals. Okay, just these are very light values and pressure. Okay. Now one more idea I want to give you is this. If you want to compute RMS value or MS value, one thing is the frequencies must be incoherent, not the same. So if I have a frequency A1 sine omega t and A2 sine omega t, and I am trying to find mean square or RMS value, you have to first combine and it becomes A1 plus A2, okay, and then it will become A1 plus A2 by root 2, okay. If they are incoherent, it becomes square root of A1 square by 2 plus A2 square by 2, okay. So it is different, okay. The other idea I want to give you is that in dB addition, suppose somebody says that we will add 80 dB to, or 80 dB will subtract 80 dB. It is not 0 dB, okay. So we are adding 80 dB, which is loud sound reference to 20 into 10 to the power minus 6 pascals, and we are adding to that minus 80 dB, which is much quieter than 20 into 10 to the power minus 6 pascals, okay. So it is, so this is negligible, so it is, this is approximately 80 dB, okay. And the other is in dB addition. If you get same values, you get an increment of 3 dB. These are quick ways of adding dBs, okay. So I will close the lecture here and we will continue in the next class.